Hello everyone and welcome to the channel. In this video, we'll take a look at the reset of the CPU and build a power-up reset circuit using a supervisor IC. I hope you enjoy! Okay, so in the past two videos, we've been building this clock module and it works pretty well. One of the things I want to add is I want to be able to set which mode and which speed the clock runs at on reset. For that, we need to talk about the reset circuits. The CPU is also going to need a reset signal. So let's build the reset module. So let me create a new sheet for the reset module. And so this module will output the reset signal, which is going to be active low. So now we should be able to import it. There we go. And add a label. And this reset signal is going to go into the reset pin of the CPU. So let's take a look at the datasheet of the CPU and see if there's anything we should keep in mind while designing the reset circuit. So I have here the datasheet of the microprocessor. If you go into the description of the reset pin, it says that the reset is active low and it's used to initialize the microprocessor and start the program. The reset input has hysteresis, which means it's a Schmidt trigger input. We could use a simple RC circuit in order to reset the CPU on power up. It also says that the reset signal must be held low for at least 2 clock cycles after the power supply reaches operating voltage. So what does this mean? So from the moment you turn on the power supply, assuming this is the time here, and let's say here switch the power on, the voltage of the power supply will take some time to ramp up until this is 5 volts. The behavior of the CPU is only defined until 4.75 volts. And so what you want to do is to have a reset signal that is, assuming this is the reset over time. So you don't actually want the CPU to start processing in this interval before the power supply has reached the maximum of 4.5 volts here. What you want to do is to have a reset signal that is high until the point where the voltage is reached, and then you want to go out of reset. And so the CPU starts processing after the reset signal goes low, and so it doesn't try to do anything before the voltage is correct. And actually, on the CPU, the reset line is active low. This means that the reset actually looks like this. So first we want the reset to be low, and then the reset needs to go high once the power is good. And what the datasheet actually tells us is that if we look at the clock, over time, it's going to go high and low. And actually, it's also going to take some time to boot up. So we don't actually know here what the clock looks like, but the circuit that is driving the clock is also going to take some time to boot up when the power is starting. And so what the datasheet tells us is that once the power is good, we need to keep the reset low for 2 clock cycles. This is 1 clock cycle, and this is another clock cycle. And only here can we take the CPU out of reset. So we're going to need another signal. This is what I'm going to call reset. The other signal that we were talking about before, I'm going to call this power up. And so the reset signal needs to be low up until 2 cycles have passed after the power was good. This is what we need to build. The datasheet tells us that the input of the CPU, which is called reset bar, actually has a hysteresis input, which means that this is the way it looks like inside. So there is a Schmidt trigger, and they talk about an internal pull-up resistor going to VCC, and this is good to the resets of the CPU. They say that we could put a capacitor here to ground, and using the active pull-up, we could charge this capacitor. And so on power-up, this is what it would look like over time. So the capacitor would charge, and then at some point, the Schmidt trigger would trigger, and so then the reset would change state. And if you make the capacitor large enough, you can ensure that this interval here is longer than 2 clocks. Then you can be within the datasheet parameters. However, this is not going to work for us because I would really like to have access to this reset signal here for other devices. This works if you only have the CPU to reset, but we're probably going to have other devices, and so we need to build our own circuit for this. And so one simple way we could build this is to take a capacitor, going to ground, with a resistor, going to VCC, and then this we would put into 74HC14, which we've already used for debouncing. So we have a bunch of those available. And this is an inverter. This would be an active high reset. The capacitor is charging here. The voltage is like this. And then since this is an inverter, we would here get first high and then low. So in order to get an active low reset, we need a second inverter here. And then this is our reset signal. So you could definitely build this, but I don't actually have a 74HC14 on the CPU board. There's also the question of how we do manual reset with a button. We would probably need to change this circuit a bit. Yeah, so what I'm going to do instead is I'm going to look at a pre-built IC for this purpose. And so that's called a supervisor IC. So the supervisor I'm going to use is the MAX705 from Maxim Integrated. This circuit is going to provide 4 functions. The first one is going to be a reset output during power up, power down, and burnout conditions. So it's going to monitor the voltage and ensure that if the voltage drops below a certain threshold, then it's not safe for the CPU to continue processing, and it's going to reset it. The same thing goes for the power up condition. It's going to wait until the power is high enough in order to let the CPU run. The second functionality is going to be useful, but I'm not going to talk about it today. It's the watchdog output that goes low if the input has not been toggled within a few seconds. And so you would use this in order to make sure that your CPU doesn't go into an infinite loop. So that's going to be useful when we get to programming the CPU. So I'll talk about it then. The third feature here is power fail warning, for example, a low battery detection. So I'm not going to use this because I don't plan on running the CPU on a battery, but you could definitely use this in order to tell you when the battery is running low. And then the fourth feature is manual reset inputs. And so we're going to use this to put a push button reset on the CPU. On the bottom right here, you can see a typical operating circuit and how it is connected. So you can see that 5 volts goes into VCC of both the MAX705 and the microprocessor. The reset line is connected directly to the reset inputs of the microprocessor. And then the WDO, PFI, and PFO we're not going to be using for now, so I'm not going to talk about them. And the last thing is you're going to need a push button connected to the manual reset. So let's go into KiCad and see what it looks like. So I have here my reset module. Let me just set the page settings. And so we already have our active low reset output set here. Let me add the MAX705. Doesn't look like the MAX705 exists in KiCad, so I'm going to need to create a symbol for it. Okay, so this is our MAX705. So we need VCC and ground. Then the active low reset is going to be the reset output of the MAX705. The watchdog we're not going to use for now. Neither are we the power fail monitoring. And actually, let me edit this Power fail monitoring we're not going to be using, and then the reset is here. And then on a manual reset, we're going to put a push button that we're going to call reset, going to ground. So this is it. So this is going to be generating a reset pulse as long as the power is below a certain threshold. If we look at the datasheets, we can see that the reset threshold for the Max 705 is typically 4.65 volts, and it's a maximum of 4.75, which is good because if we look at the datasheet of the CPU, in the DC characteristics, we see that the minimum voltage it's specified at for 5 volts is 4.75. By setting a reset threshold at a maximum of 4.75, we are guaranteed that the supervisor will not reset the CPU when it's in the usable range. And we see here that the pulse width of the reset signal is going to be typically 200 milliseconds. We are within spec if all the circuitry has the time to boot in 200 milliseconds, which is pretty much guaranteed. And then because we need 2 clock cycles to happen within the first 200 milliseconds, then we know that the minimum frequency we can run the clock at is 10 Hertz. Of course, this is not what we're doing. Remember, the slow clock can go as low as below 1 Hertz, and we also have the pulse clock. If we don't pulse the clock manually during this delay, then no clock cycle will happen during the reset, and so the CPU will not register it. So we need to add some more circuitry in order to work around this. Let's say that this is our power up reset. So it's going to be low for a while, and then it's going to go high. This is the time. This is the voltage. And then let's say that we have our clock here. That goes like this over time. So what we want is, after the power is good, we want 2 full clock cycles. So that's 1 and 2. And then after this, we are okay to bring the reset high. So technically, this is not 2 clock cycles after the power is good. It's 2 clock cycles after the end of the reset pulse by the Max 705, which happens 200 milliseconds after the power is good. But that's a good enough approximation for my purposes, and so I'm going to roll with that. And so in order to do this, I'm going to add 3 flip-flops between power up and resets. They're going to trigger on the positive edge. So as you can see, we need 3 of them in order to do what we want. So let's add it to the circuit. So the reset is going to be at the end, and so we are going to chain the flip-flops to the reset output of the Max 705. We need a clock input. That goes into the flip-flops 3 times. Then the set input is going to be a no connect. The inverted output is going to be a no connect. And actually, let's put this away a bit because I want to output this signal. So this is our power up signal. We also want to reset all the flip-flops when we are powering up. So this ensures that as long as we're powering up, the reset output stays low. And then once this goes high, it takes 1, 2, and 3 positive going edges of the clock until the reset goes high. So doing this, we were able to delay the reset for 2 clock signals. When we're on the fast clock or a relatively fast slow clock, we're not going to see this delay because it's going to be instantaneous. But when we have a slow clock or we're in the pulse clock, then we're going to need to wait until at least 2 clock cycles have elapsed in order for the reset line to go high again. So let me annotate this. We have 1 spare flip-flop. We need 2 decoupling capacitors. No, 3 actually decoupling capacitors. And then we need the 2 power supplies of the flip-flops. I'm going to connect all the unused inputs of the last flip-flop to VCC. Its outputs are going to be no connects. Then we need to connect the power supplies to VCC and ground, and also the decoupling capacitors. So let me clean that up a bit. There we go. And I'm actually going to export the power-up signal as an output so that we are able to use it elsewhere. One thing that also might be useful is to have an active high reset line. So I'm actually going to copy this here, and this is going to be our active high reset, which could be useful. And then what I'm going to do is I also want to add a reset LED. However, I don't want to drive it from the main reset line because it's not good practice to drive LEDs from your signals. So I'm going to take the spare gate that we have here. I'm going to use it to duplicate the last flip-flop here. So if I do it like this, and if I connect it identically, we can use its outputs in order to drive a LED. So I'm going to use the active high output here and a resistor going to ground. There we go. So one thing we can also do is add a small capacitor in parallel with the reset switch. And so what that is going to do is going to help prevent parasitic resets. So that means that if there's any noise on this line, it's going to be dampened by the capacitor. So let me annotate everything and go back one level and import my pins. So the clock is an input. Then we have the power up reset and the active high reset. And those I'm not going to connect, but we do need the clock as an input. There we go. Actually, I just noticed a mistake here. Those shouldn't be no connects. They should be tied high. And this should go to VCC. There we go. So let's implement this on a breadboard and see if it works. So this is our breadboards where we left off the last time. I'm going to focus on the clock for now. And I'm going to add a new breadboard. So this is our max 705. I'm going to add it here, as well as the manual reset button. So we need a decoupling capacitor. I never actually know which sides of these are connected. Okay, so the top and bottom are connected. So we need to connect the button to ground and to pin 1 of the 705. Then it needs power and ground. And so that's pin 2 for power and pin 3 for ground. So we need to connect the power fail input to ground as well. I made an error in the schematic, but pin 4 should go to ground. And then our reset signal is on pin 7. So let me just add a LED for now so we can see when it's resetting. And let's test this. Okay, so if I press the reset button, then as you can see, there is a reset pulse that is generated. And if I unplug and plug the power supply, you can see that the reset pulse is also generated. So let's power up the oscilloscope and see if we can show this on a graph. So in yellow, it's going to be the power. And in blue, it's going to be the reset signal. So it looks like my power is really noisy, but that's just because of the oscillator. So let me just remove that. So at the moment the reset is low and the power is high. I'm going to trigger on the second channel on the rising edge and do a single capture. Okay, so this is the falling edge of the reset signal. Let me zoom out a little bit. There we go. So you can see that as I press the button, we generate a downgoing pulse. Let's measure it. And the width is around 300 milliseconds. So this is working. Now let me do the same thing with the power. So I'm going to trigger on the power rising and do a single capture. There we go. So here we see when I plugged in the power, we generated a pulse that was around 200 milliseconds in the reset signal. Let's zoom in on the beginning of the power signal. So you can see that it kept the reset line low when the power supply was booting, and then as it was stabilizing. Let's redo a single capture so we have more precision here. There we go. So there's some oscillation in the power and then the reset stays low. Okay, so this seems to be working pretty well. I'm going to try one more thing, which is to reduce the voltage on my power supply. And so we're going to be able to see the reset line going high. So if I drop it to 4 volts, you see that the reset line just went low. And if I bring it back to 5, then it goes high again. That's good. So it seems to be working well. So let's add the flip-flops now. I have here two 74 HCT 74 flip-flops. They need power and ground. And decoupling capacitors. Now we need to connect pin 1 and 13 of both chips to the output of the 705. There we go. And also to pin number 2 of the first flip-flop. There we go. We need to connect pin 4 and 10 of both flip-flops to VCC. There we go. Then we need to change the flip-flop. Pin number 5 is going to pin 12 of the first flip-flop. Pin number 9 going to pin 2 and pin 12 of the second flip-flop. So, okay. Then we need the clock. I'm going to put the LED on pin number 8 of the second flip-flop. So the clock is going between pin number 3 and pin number 3, pin number 9 and pin number 9, pin number 11 and pin number 11. And then they need to be both connected together. There we go. So now we have the clock in all 4 flip-flops. And so I'm going to need to get the clock from just above. And so that is where the LED is at the moment here. Going down. And I'm actually going to power the LED from the other output of the flip-flop. so it doesn't mess with the clock. I should probably use the spare flip-flop here to drive the LED. I'll do that later. I believe this is everything. And I'm going to add an LED to the power-up signal so we can see what it looks like. There we go. So now the clock is in pulse mode. Let's try to reset manually. So I'm going to press the button. Okay, so I did a mistake here. Okay, so this should be working now. So if I reset, then the input of the first flip-flop is high. I need to clock it once with one rising edge to go here, a second rising edge to go here, and then a final rising edge to go here. So that's good. Let me remove this. So let's try again. So I reset, and then I have 1, 2, 3 rising edges, and then the reset goes low. Okay, so this is great. Let's try the power on. So power on reset. I need to clock for it to disappear. So this is working well. Now the next thing I want to do is to be able to set which mode the clock boots in, because right now when I plug in the power, it's random. I mean, it's pretty constant going into the pulse clock, but you can't actually count on that. So I'm going to use this new reset signal to drive the reset lines of the flip-flops in the clock. Okay, so as I said, we need to connect the PowerFL input to ground. Been reading up on labels in KiCad, and I think I've been using them the wrong way. I've been using global labels, which are shared between all the sheets in the project, which I don't want. So I need to change this to local labels instead. So let me do that now. Okay, so I don't think this is strictly necessary, but I like it because then I have all the sheet IOs in one place, and within my schematic I'm only using local labels, so I think it's clearer that way. Let me edit the other sheets to match. And I think it's pretty nice that now the bar over the inverted signals doesn't overlap with the box arrow that was around the global labels when you connect them to pins. There we go. So these are all my labels converted. So now I'm sure that signals don't conflict between sheets. Okay, so there is one simplification we can do to this circuit, and that's because we are using the same clock for all the flip-flops. We can use a chip like the 74HC175, which is a 4-bit D flip-flop. So it contains 4 flip-flops clocked with the same clock pulse and also with identical reset. So we can replace the two 74HC74 with a 74HC175. Okay, so now the reset circuit only uses 2 chips, so that's pretty good. Let me make the changes on the breadboard. Okay, so I have here 74HC175. Let's replace those 4 flip-flops. So it needs power and ground. The clock needs to come in on pin 9. So that's here. There we go. The power up signal needs to come in on pin 4 and pin 1. Then we need to connect pin 2 to pin 5. And pin 7 to pin 12 and 13. Then our reset LED is connected to pin 14. Actually, I don't have a ground here, so I'm going to connect it to pin 15 inverted. Let's see if that's the right way later. And then our reset is on pin 10 and 11. Okay, so let's see if it works. Good. So this seems to be working. Okay, so in this video, we've added a power on reset circuit using a Mach 705 supervisor circuit. And we've made sure that the reset is kept low for a few clock cycles so that the CPU can register it, even if we're on the pulse clock or the slow clock. In the next video, we'll go back to the clock and we'll make sure that the power-up behavior is configurable, and we'll also work on clean clock switching. So I hope you enjoyed this one. Let me know in the comments if you've got any questions or feedback, and I hope to see you in the next one. Goodbye.